Hello everyone, I hope you are enjoying your day. My name is Mahmoud Abido. I am a PhD student in Mechanical Engineering Department, University of California, Merced. Today I will present the paper titled with Seasonal Challenges for a Zero Carbon Grid in California. The main question that we are trying to answer is how can 100% renewable energy grid, or what we can call zero carbon grid, be achieved in California? And when will be the highest risk of electricity generation shortage, or what we can call resource adequacy challenge? We used a high-level energy balance approach in which we are balancing the generation with the load, with a storage connected to the grid to be used in case of extra generation and generation shortage. Also, we have surplus energy in case of having extra energy with a full storage. But this approach didn't include the transmission constraints. We applied this methodology to different scenarios using different added generations from various renewable resources or a combination between two renewable resources like solar and wind. Finally, we will state our key findings related to the time of the year in which we have the resource adequacy challenge. Currently, the electricity in California is generated using renewable resources like solar, wind, hydro, and other renewables like biomass and geothermal, and other resources like thermal, nuclear, and imports. But in a 100% renewable energy grid, we will have only renewable resources like solar, wind, hydro, and other renewables. In 2019, the annual renewable resources generation covered about 40% of the annual load, as shown in this figure. The vertical axis shows the load and generation in gigawatt, the gray color for load, and the red color for renewable generation. So the available renewable resources are not enough to drive a 100% renewable grid. So we should build more renewable resources. But which renewable resource is better to invest in California? Solar is cheap and available most of the year in California, while wind is not so great as it increases during the summer and decreases during the winter, exactly as solar as shown in this figure. But it may be better in other states like Colorado. Offshore wind is available, but it is expensive relative to the other renewable resources, especially solar. Large hydro is not expandable, especially with the possibility of severe droughts. Other renewables, like geothermal, may be used as a flat generation that will be constant along the year, but the pathway to expand them is not clear yet. So we started focusing on solar generation as it is the most practical solution to achieve 100% renewable grid in California. This figure shows 2019 relative solar generation, and it is clear that the generation is variable every day along the year, and the daily winter generation is about 50% of the daily summer generation, as shown in this figure, where the red color for summer and the blue color for winter. If we add to the 2019's renewable generation about 4.6 multiples of the 2019 solar resources, we will balance the annual generation and the annual load. As shown in this figure, where the vertical axis is the load and generation in gigawatt, we still have a problem during the winter, as the generation is not enough to cover the winter load. But we have an extra generation during the summer, as the generation is more than the load. So we should use a storage that can store the extra energy during the summer to be used during the winter. Here, the blue shade shows the charging and discharging periods of the storage. Negative means discharging and positive means charging. So it will be in a discharging mode during the winter and in a charging mode during the summer. It acts as a seasonal storage that stores the summer energy to be used during winter. So the state of charge of this reservoir will start with a specific value, as shown here on the vertical axis in terawatt hour. Then it will be discharging during the winter, January, February, reaching to the minimum state of charge in March, which will be the most challenging period during the year. After that, it will start to charge during the spring and summer, then discharge again during November and December. The charging and discharging process is a daily process, as the reservoir is charging during the day from sunrise to sunset and discharging during the night. Here, the storage size is about 25 terawatt hour, which is about 2 trillion phone battery. This is a very large battery that is difficult to be applied in a cost-efficient way. So we should figure out how to reduce this storage size. To reduce this storage size, we should increase the generation. Increasing the generation by 30% decreases the storage size to half. And this result is not only for 2019, but also for the rest of the years like 2016 and 2018, as shown in this figure. Increasing the generation also affects the date in which we have the minimum state of charge. It is shifted about 1 month from March to February, and it will be shifted more to January if we increase the generation more. But winter is still the challenging season in which we are expecting resource adequacy challenge. The same calculations were applied for years 2015 to 2020, and it showed that the seasonal challenge will be in winter for all the years for a solar dominant grid. We studied also different scenarios to achieve zero carbon grid. First, by adding generation from a single renewable resource to the grid. Previously, we studied adding more solar generation like the yellow curve in these figures, in which we have the state of charge of the storage in terawatt hour. The left one has a total generation of 105% of the load, and the right one has a total generation of 135% of the load. Here, we are studying adding more onshore wind, which are the cyan curves, and the offshore wind, which are the blue curves, and a flat generation like geothermal generation, which are the green curves, while comparing these to the solar dominant scenario. So for year 2018 as a sample, winter will be the challenging season for a solar dominant grid and for an onshore wind dominant grid. While for an offshore wind dominant grid, the challenging season may be during the whole year, as seen in the right figure, where we might have a risk in July, November, and maybe in October. The flat generation, like geothermal dominant grid, will achieve the smallest storage size required in both cases. Actually, these graphs helped us to understand the effect of each resource and to select the most practical scenarios. The same calculations were applied to the rest of the years for 3 more practical scenarios. In the first one, the added generation is divided into 50% solar and 50% onshore wind. In the second one, The added generation is 100% solar generation. And in the third one, the added generation is divided into 50% solar and 50% offshore wind. For the three different scenarios, the seasonal challenge is still during the winter for the years 2015 to 2020. And adding offshore wind generation to a solar dominant grid will reduce the storage size, while adding onshore wind generation to a solar dominant grid will increase the storage size. Finally, the winter will be the challenging season for a solar dominant grid in California. Increasing the generation will shift the most challenging date earlier from March to January, depending on the percentage of generation relative to the load. The seasonal storage needed to balance the supply and demand may be cut in half by building 30% more electricity generating capacity. For more details, please check the journal article, Seasonal Challenges for a California Renewable Energy-Driven Grid, submitted to IEEE Journal of Photovoltaics, and it is currently under review. Thank you and have a wonderful day.